All right, let's look at example number 2. So they're telling us that a boat travels around a circular path where the radius of the path is 40 meters and the speed is given by, actually the speed increases, so there's an acceleration. The speed increases with time, so that velocity is this function. Okay, the magnitude of the boat's velocity and acceleration are needed at time t. So we need to know in 10 seconds what is the velocity and acceleration. All right, so the plan is to basically find the terms at 0 and 10, or any other points that they're asking us. And also we need to calculate the tangential and normal components of the acceleration. So we know that the component of the tangential velocity is equal to the instantaneous velocity times the unit vector in the tangential direction. So if the expression they're giving us is v equals 0.0625 times time squared, this is already in a function of time. It's not a function of distance. It's not a function of x or s. So we don't need to do the chain rule. The only thing we need to do is compute. Well, actually, if we want it, we can find the displacement or anything by integrating. If you integrate this, you'll find the displacement. If you derive this, you find the acceleration. If you integrate this with respect to time, you'll find the displacement. Okay, so all we need to know is the velocity at time 10 seconds is equal to 0.0625. 10 squared is 100, and that is equal to 6.25 meters per second. Okay, very simple. So the acceleration, this is a formula that we already saw before, is the change in the velocity with respect to the tangential coordinates and the velocity squared divided by the radius times the normal unit vector. So let's go ahead and find that the tangential component is dv dt. So basically we just need to compute that derivative, and it's 2 times 0.0625 t, which is equal to 0.125 t. All right, and this is meters per second square because this is an acceleration. Okay, so now at 10 seconds we simply have to evaluate the function, and that is that times 10, which is, this is, if it's 1 will be 10, so it's 1.25 meters per second squared. All right, now the normal component is very easy because the normal component is simply the velocity squared divided by the curvature, the radius of the curvature. And the velocity squared is 6.25. 6.25 squared divided by the radius, which is 40, always right here too, 40. Then the normal acceleration is 6.25 divided by 40, so 6 times 36, whatever this is, divided by 40 is less than, is it less than 1? Yeah, is 0.9766 meters per second squared. But this is the normal component of the acceleration, right? So we have a tangential component and a normal component. That's why when you're in a car, and even though you're trying to sustain the velocity constant, that's 60 miles per hour, and you have a curve, you can feel how the car is trying to go out of the curve. That's why roads have to be designed with certain slope, because in a curvature, the change in direction will provide an acceleration term. Okay, so the total acceleration, the magnitude of the acceleration is the square root of the tangential velocity acceleration squared times the normal acceleration squared, and that basically is, this is 1.25 and this is 0.976. That term is 1.59 meters per second. So very simple. If it's in terms of time, you simply derive, um, and then you already got the acceleration. And if it's the normal component, you simply have to apply this formula of velocity squared divided by the radius.